All right. Well, what we're going to do right now is take a look at this particular learning outcome. We want to be able to convert points and equations between polar and Cartesian coordinates and equations. So in particular, we're going to look at equations right now, polar equations and Cartesian equations. And in order to be able to do any of this, we have to know how are these coordinates related to each other. And so by using, you can draw this in the corner here, using a right triangle, we see that the x and the y coordinates of a particular point have a relationship between the r and theta coordinates, polar coordinates of that point. And by doing a bunch of trig, we can come up with 4 equations that I like to use to do these conversions. We can see that x is equal to r cosine of theta, y is equal to r sine of theta, x squared plus y squared is equal to r squared, and finally the tangent of theta is y divided by x. There are other relationships, other trig combinations we can come up with. However, these are the 4 that I typically use for these problems. So in this situation here, we have I believe a typo. I meant to write the square root of 3x just to make the angle a little bit nicer. All right, so in this first equation, we have y equals square root of 3x, let's say. And so let's go ahead and apply the x and y conversions. So we get that r sine of theta is equal to root 3 r cosine of theta. Okay, and I see that in this case, the r's cancel, and I can divide by cosine to get tangent of theta is equal to root 3. And I want to point out that I could have done this another way, right? I could have also divided y divided by x to get root 3. And then from this formula here, I also find tangent of theta is equal to root 3. You name it, there's a half dozen ways to make this happen for each other, from one to the other. However, at the end of the day, I need to know what angle gives me a tangent of root 3. You got technology, just do the arc tangent, the inverse tangent on root 3, and use degree mode. You'll get degrees, or if you're using radians, you'll get radians. We always answer in radians. What I want to point out is that you can, if you want to be a little bit clever, do this without technology. And if you just know sine and cosine, reference angles on the unit circle, we can observe that this is root 3 over 1. And so that's root 3 over 2 over 1/2. And so my options are either that's going to be pi over 3. You could also do 7 pi over, 7 pi over 3 or 4 pi over 3. There are other options, other angles you could use. However, we normally use a small theta value, small positive theta value if we can. So in this situation, that's the angle that I would pick for this particular polar equation. There are others, but this one works. And this makes sense because if I were to graph this, well, what would that be? Well, all I'm doing is taking the angle of pi over 3, and all these different r values give me different points on this line, which has a positive bigger than 1 slope. So that kind of matches up with this root 3x thing here. All right, let's take a look at this example over here. R equals 5 cosecant of theta. So in this situation here, again, you could do various things with, you could write r as the square root of x squared plus y squared. I think though, in this situation, actually, I know what I need to do. This cosecant doesn't show up in any of my formulas, but it's the inverse of the multiplicative inverse of sine. I can rewrite this as 5 divided by sine, and then I get that r sine of theta is equal to 5. And then all I have to do is replace that r sine of theta with y, And there I have my equation. Turns out this is another straight line. If I were to draw this, then I could draw a horizontal line, distance 5 up, and that makes sense because even from the original, if I take different theta values, like theta is equal to 0, it's undefined. I don't have any points because I'd be divided by sine of 0, which is 0, and that's undefined. But if I pick like 45 degrees or pi over 4 radians, then I get 5 root 2 right up here at this point of the line. If I plug in 90 degrees, I just get 5 divided by 1. And that's this point straight up at y is equal to 5. And you can try different theta values and see. And even the theta value, that's negative, well, I'll get you a negative r value, and it comes back over here. So that does actually work out. Let me do one more example while I'm recording here. There's another kind of go-to example. Let's do another rectangular to polar conversion. And so actually, no, let's do polar to rectangular. So I'll call this task 3 for, example. And let's suppose this is slightly different. Let's just say this is r equals 5 sine of theta. Now in this situation, we don't have the r sine of theta that we really want. We can't divide this over and use this formula as it is. However, what I would do in this situation is multiply both sides by r to get r squared equals 5r sine of theta. And if that's the situation now, I can replace x squared plus y squared is equal to 5y. And technically I'm done. This is a rectangular equation. It may not be obvious what kind of equation it is. If you want to see what it kind of is and to know how to graph it, then I would subtract this over and I would complete that square. And this would actually be, because I picked an odd number, it's a little bit gross. It's 25 divided by 4. Add that to both sides. And then I can factor out y minus 5/2 squared. And in that situation, we see that we have a circle of radius 5/2, and it's a little bit, and its center is 5/2 above the y-axis. So it looks something like, let me get a different color here and move this over a little bit, something like this right here, where the center here is at 5/2.